Hopefully you remember from circular motion the relationship between period frequency and angular velocity. If not, let's go over that right now. We got t being period as measured in seconds. We have f being frequency as measured in hertz, which is 1/seconds, so this equation should make plenty of sense. Then we've got omega, which is measured in radians per second. Now, that should also make sense because if we take 2 pi divided by radians over seconds, then we're really taking 2 pi times seconds over radians. We just flip that, and radians gets canceled out by the 2 pi, leaving us with seconds, which is equivalent to that period. So this whole equation should make sense. We can really make any of these equivalent. Now, that's going to come up quite a bit in this unit, because this unit is going to be about oscillatory motion, which is going to be motion that is regular and continuous, like the swinging of a pendulum back and forth. So I've got a pendulum with a little bob at the end of it. I can pull it back up and have it at this different position. And I can let it go and it'll oscillate back and forth between these angles. It'll move back and forth. It'll steadily lose energy just because of friction and gravitation, but in an ideal system, it would be able to swing back and forth evenly, consistently. So we're going to be able to figure out the factors that go into this kind of oscillatory motion. We also call this harmonic motion, or simple harmonic motion. You'll see that abbreviated SHM. Now, when we look at simple harmonic motion, we want to start tracking that motion, because it's not just going to be, we'll have a mass on a spring. And it's not like we're going to be able to just compress that, pull it in, and then let it go and have it go flying. If it's connected to that spring, it's going to move out. So we'll have a box that'll come out this way, up to this point, and then the spring will pull it back in. It'll come back here to this point, and it'll move back and forth like that. And so that motion is moving back and forth. And so if we graphed that displacement over time, it would be back and forth. And that becomes really important. This sinusoidal wave is very important. And you may have heard that term before, you may not have, but effectively it is the sine wave function. When I take the sine of an angle, well, those angles all correspond to points on this waveform. If we were to graph a sine function, we would get a wave. In fact, let's go ahead and do that. We could say y equals the sine of x. And we're going to get a pretty solid value for that. Now we can make adjustments to this by saying 5, 10, 3. We can also make adjustments to this by saying maybe we're going to say x minus 5. See how it shifts to the right. And let's actually make a dial here, make a slider, so that we can see how this shifts. As I move that slider, my wave shifts to the right and to the left. So this is going to be the base equation for the equation of a wave, which we're going to need to be able to use in this unit. So you probably won't be familiar with this, but we're going to use it to predict different positions at different times. And so the version of this that we're going to use is going to look like this. It's going to be x as a function of time be equal to a sine of omega t. Now what this means is that a is my amplitude. This is going to be how far back I'm pulling something. So if I move this mass on a spring, if I pull it all the way out, well, this distance right here, this between there and there, that would be my amplitude. So it's going to be a modifier on that sine wave. We saw that made the sine wave bigger or smaller. A higher amplitude would make those humps bigger, which should make sense. And then we're going to have omega, that's going to be our angular velocity. And our t is going to be our time. Now those are concepts we're familiar with. We're just putting these together in a new way. X is going to be our displacement. And then this t right here, this is time. And this is just saying that this x is going to be dependent on the time. What we're really saying here is that if I graphed this, I would graph it so that x is on my y-axis and time is on my x-axis. And that this amplitude and this angular velocity, those would just be modifiers to this function. Those would be like the slope. If I were to write the slope-intercept form, m and b, those would be like my a and omega here. Now, we are going to use this equation in different ways. We might need this to be equal to this guy, this angular velocity. We might need that to be equal to a period or frequency. And so we might rewrite this in order to make my frequency or period fit into that. So let's use this equation up here and see what that would look like. So since omega equals 2 pi over t, I can substitute this 2 pi over t in for that omega. And so I'll rewrite this. And so we can see that right in there. And we could also use frequency. So now we can substitute 2 pi f in for that same equation. And so we have three versions of really the same equation. And we'll be able to switch these out when we need to. Now, we're not going to get too heavy into the wave equation. I'm just spending more time on it because it's something that's likely unfamiliar to you. What we're really going to be more focused on is going to be the period of certain oscillators and how that's determined. And we'll be able to determine that experimentally. There's one more factor we need to consider. A pendulum is pretty straightforward in how it moves back and forth. I mean, it's got a force of gravity that's trying to pull it straight down, and we can calculate that using an angle. That should be something that it might take a little bit of time, but we could at least figure it out. It might take a little bit of effort, but we could figure it out. But we're also going to use a spring mass system. Now, we haven't covered spring potential energy yet, so let's cover that here. What is that going to be? Spring potential energy is going to be represented by something called Hooke's law. The history of physics is very interesting. Hooke was another scientist right around the time of Newton, and he and Newton actually had correspondence. He criticized one of Newton's earliest works, barely criticized it, as in said, I'm not sure that this is actually how this works, and Newton's response was to write a flaming report on how Hooke is definitely an idiot. Newton seemed to be a fairly petty fellow. But Hooke had his own successes, and one of those is Hooke's law. Hooke's law tells us the force of a spring, and that is going to be just K times X. Now, K is going to be a spring constant. It's going to be an amount of, it's basically a force that the spring is going to apply when we pull it back. If I have a spring and I pull it back so that it's stretched out twice as long, and then I let it go, it's going to have a force. It's going to be pulling on a force. It's going to have a force that's going to be a function of that K. And if I were to graph that out, force here, X here, I graphed it out like this, my slope would be my K. So that's really all this equation is saying. It's really just y equals mx plus b. However, we can also get an energy version of that. We can make some spring potential energy. And if we do that, it would be multiplying both sides by x, right? Well, that force times a distance, well, x is already a distance. And so we're actually going to take the area under this curve, and that's going to be our spring potential energy. It's an integration, and it's one of the only ones that looks a little bit different. It's going to be 1/2 kx squared, because the force here is already kx. So if I take force times distance, well, my force is already kx, right? And then I need to take the area under this curve, so I need to take x again, and then 1/2 because it's a triangle. And hopefully that makes sense. Really, this height here, the height of this triangle, is kx. And the base of this triangle is x. So I'm taking kx times x times 1/2 because I'm finding the area of that triangle. So 1/2 kxx is 1/2 kx squared, just like that. So let's make sure we have a decent understanding of K here. If I have two springs, let's give it that one, and let's give it one that's clearly a little beefier. Even if they're the same length, let's pretend that these are the same length, what's going to be my difference in K values? Well, the stronger the string, the larger the K value. So here, if I pull this spring out, if I pull it out a distance x, and it doesn't matter if I pull it out or compress it, either way it will still be a distance of x, it's going to give me a force based on that K, and that K might be only 2 because it's a smaller spring. But if I have a larger string, a beefier string, if it's harder to pull out, and I pull it out the same distance, K might be, say, 7. So now if I pull it out that same distance, suddenly my force here is 7x, where here it's only 2x. So the bigger the spring, the harder it is to pull that out, the bigger that K value is. So that's what that K is really standing for. It's how difficult is it to stretch or compress this spring. K is really a measure of that. And then we're able to figure out a force from how much it's stretched out and how strong that spring is. So those are the general equations that we're going to be using in this unit in order to invest our simple harmonic motion. Hopefully these equations make sense. You should be able to do a little bit of algebra with Hooke's law and with our period, frequency, and angular velocity. You will not need to do any algebra with the wave equation yet. We will build up to that. You'll be prepared for it. It'll be okay when we get there. But for now, we really just need to be able to do kind of this simple algebra here and here in these two places. And then we'll be able to do some labs and calculate some simple harmonic motions.